will talk to you about a series of work. It will be a kind of overview, actually, on these problems related to trapped fermions. I chose, given the audience, maybe I chose to put the emphasis today on the connection to random matrix models, which might be of interest for several of you. These works actually have been done with these gentlemen here, especially David Dean from Bordeaux, Pierre Ledoussal from INS, and Satya Majumdar from LAPTh in Orsay. And part of this work was done with my PhD student, Bertrand Lacroix, who is now a postdoc at the Weizmann. And, so this is just a couple of references that I give you here. We started to work on this problem basically in 2015, where we exploited this connection to GUE, the Gaussian unitary ensemble of random matrices, and we tried to go beyond that in a series of works, and eventually I will try to discuss in detail today what these multi-critical models are. And we recently, relatively recently, wrote a review in GPhys. So part of the motivation for these works actually come from the fact that, as you know, there had been tremendous recent progress in experimental manipulations of cold atoms, and this allows to investigate in quite detailed way the interplay between quantum and thermal fluctuations in these low-dimensional systems, and in particular at very low temperature. Now, as you know, as you probably know, a common feature, common properties of all these experiments is that if you really want to see your and observe your gas of particles, you need to confine them in order that you can perform some measurements on them. And to do that, typically what you have to do is to confine them within a potential, say, V of x. What I was saying here, what I mentioned is that indeed that we have now, or actually our colleagues, experimentalists, they have now very sophisticated tools to have access to the properties of these atomic gases, and the oldest one somehow, and the relatively standard one by now is the measurements, which are these time-of-flight experiments, which essentially allow for direct measurement of the momenta of the fermions. So this is just a plot here from the group of Ingusio in Florence, but there are tons of papers around these types of experiments. And in fact, more recently, there are several groups who devised what they call this quantum Fermi gas microscope, which actually allows for direct imaging of the positions of the particles. Okay, so they are really able to make some snapshots. So this is a snapshot of a gas of lithium, which was performed in the group of Markus Greiner at Harvard. And that means that you are really able now to measure and to study in detail the spatial fluctuations of these particles, and you would like to understand the statistics of this cloud of points. Okay, so you have basically these two types of tools: one in order to measure the positions, and the other one these positions and the momenta. Okay, so which are, so to say, there is of course some duality via some Fourier transform between the two, and I will come back to this later. But I think that was part of our motivation, that indeed one can now have quite detailed statistics about the positions of these points, and we would like to understand them better. Now, of course, we were not the first one to study this rather simple model of fermions, non-interacting fermions, in the presence of a potential, and but nevertheless, most of the available theory actually deals with what happens in the bulk of the gas. That means in the center of the trap. And for that, there are actually a lot of theories available for that. One is typically the local density approximation, basically, that amounts to say that if you are close to the center here, you have the density is essentially uniform, and you have a model which is translationally invariant, at least if you look at it locally, and that means that to a large extent, if you focus on the bulk properties, you are not too much sensitive to the curvature of the potential, whatever this potential is. And that means that much less is known about what happens at the edge of the gas, okay? And there were several reasons for that. I mean, the first one is that indeed, when you are here, you need really to take into account the curvature of the potential, so that you have now to deal with a system which is not translationally invariant, and this has been we need to take this into account. And on the other hand, as we will see, it turns out that the density here is also much smaller than what it is in the bulk, and that means that this is also a region where the system is much more sensitive to fluctuations, either quantum fluctuations or thermal ones. And in fact, this was already pointed out in this nice paper by Walter Kohn, who pointed out that indeed the traditional density-based, so that means this local density approximation type of theories, they actually do not hold for inhomogeneous system, and they are clearly inappropriate to describe what happens near the edge. And so that was really our motivation, to try to have to have a theory and tools to understand better what happens there. And what we realized, and that's what we try to push quite far, is that the random matrix tools are actually the ideal ones to study what happens near the edges. And the outcome of these works is that if you really look at what happens at the edge, it turns out that there is a very interesting new physics induced by the confinement, and that's really important to take carefully into account this inhomogeneity, and as we will see, this leads to a quite nice and interesting universal edge properties. So that was to a large extent our motivation. Now, I mentioned random matrix theory. Why is it so? Well, as you probably know, the simplest model for a confined system with fermions, where you see this connection to random matrix theory, is the one where you just look at the quadratic potential. And in this case, as you probably know, and I will come back to that in a minute, it turns out that at zero temperature, there is a one-to-one correspondence between the positions of the fermions and the eigenvalues of random matrices belonging to a certain ensemble, here this Gaussian unitary ensemble. And that was for us the starting point from that, because we had already worked on random matrices for quite some time, and this was some kind of very interesting and nice playground to develop these random matrix ideas in that context. Okay, so that will be the outline. So I will just start with a description of this connection between the free fermions in 1D and at zero temperature, and this simple random matrix model. I will then show you that it's not only GUE that can be implemented in fermionic systems, but you can actually basically implement all the classical matrix ensembles, and I will discuss these hard box potentials quite quickly, and then I will come to this point, which deals actually not with the positions, not with the statistics of the positions, but the statistics of the momenta, and I will show you how this is connected with some multicritical matrix models. So let's move on, and let's look at this textbook example where I just want to describe n free fermions, so non-interacting fermions. And I will also forget about the spin, so I will consider spinless fermions. So I will just assume that they are projected in one of the two states, up or down, if I have electrons in mind. And I just want to compute the wave function of this simple system. Okay, so let's start with a simple single particle. Well, again, this is a very well-known problem. You can write the eigenvalues, the eigenvectors, sorry, of the Schrödinger operators in terms of these Hermite polynomials. Okay, and indeed your wave functions are indexed by k, where k is an integer, and this index k is here in the Hermite polynomial, and of course the energies are just given by this h bar omega k plus half. So this is for a single particle. And if you have fermions, well, what will happen is that if you have n fermions, and if you look at the ground state, then you will put, again, I look at spinless fermions, then you will just put the first fermions there and so on. Okay, so we'll just have this kind of Fermi C, and the way you construct the wave function is by just by writing the Slater determinant corresponding to these single particle wave functions. Okay. Now in this case, that's the determinant that you have to deal with, and if you just do some simple manipulation of this determinant, well, you see that you can just get out these Gaussian prefactors, and then you are left with the determinant of these Hermite polynomials. And as it is well known, now if you start to make some combination of columns or lines of this with this determinant, eventually you can write it up to some constant, up to some prefactor. This determinant will simply be this van der Mond. Okay, sorry. Now this is by 0. Okay, so that's yeah. Okay, so. Let's see. Yeah, it seems. Yeah, it does. Okay, sorry. Okay, yeah, so that's the wave function psi 0. Now, of course, the good object is the modulo square of this that will give you the joint probability density functions for the positions, okay? And of course, if you square this, what you get is precisely this expression, okay? So I have this product of Gaussians, and I have here a term which is van der Mond square, and you see that, of course, this means that the positions are actually correlated, although, of course, they are non-interacting, but that really comes from the Pauli exclusion principle, right? Now, it turns out that this quantity here appears in a matrix model, so let me just recall you where it does come from. So if I just consider a matrix J, which is a n by n random Hermitian matrix, that means that I take all the entries, both real and imaginary part, as IID Gaussian random numbers. Well, it's well known that, of course, it's Hermitian, so it has n real eigenvalues, and you can compute explicitly the joint distribution of these eigenvalues, which turns out to be exactly given by that. And so you see that there is indeed a one-to-one correspondence between these two things. And that means that the positions, again, as I said, of the free fermions, in this case, for the quadratic potential, they behave statistically exactly as the same way as the eigenvalues of these GUE random matrices. And recently, during the last 10 years, say, many people actually have used these random matrix results to explore new questions in the fermion problem. So let me just remind you what we know about this RMT, this random matrix model. Well, the first thing that you may ask is about the density of the free fermions. Okay, so if I just look at this quantity here, evaluated in a ground state. Yeah, so here I will discuss only zero temperature properties, okay, until the end that I will deal with ground state properties. Then it's given by the famous Wigner semicircle, okay? So that's simply this quantity here. So you see that You see the scaling here, so that means that the extent of the gas is of the order square root of n, and it's simply given by this semicircle, right? Now, it's well known also that if you look at the local statistics of these eigenvalues in the matrix models or the positions of the fermions, it's well known that there are actually, in such models, that there are basically two different regimes. The first one is what happens in the center of the trap, and that's the one that I was discussing right at the beginning, and which is relatively well described, which is well described by the standard theories like Thomas Fermi or local density approximation. And that's the bulk, okay? So in the bulk, basically, one can easily estimate the interparticle spacing. There are several ways to do that, but typically, as I said, you have n particles and the density extends over a domain which is of order square root of n, and so the typical distance between particles is simply 1 over square root of n. So that's the bulk regime, which is very well understood. Now, at the edge, as I said, the density turns out to be much smaller. Eventually, it really vanishes if you look simply at the profile that I wrote here. And you can estimate, you can easily estimate the interparticle distance by using an argument which is very frequently used in the context of extreme value statistics. But basically, what you are saying, what you want to say, is that what you will say is that, okay, suppose that I want to estimate this this length at the edge, which is L edge here. Well, what I will say is that, roughly speaking, I want that the number of particles in that interval is typically of order 1. Okay, so you want just to say that there is one particle within this range here, and because you have a square root singularity of the density, right? Here you remember that you have this semicircle here, which vanishes as a square root. If you insert the square root in this expression, what you will get is that the typical length at the edge is of the order n to the power minus 1/6. Okay? And that's, of course, well known in random matrix theory. I will come back to that in a minute. But that clearly says, indeed, that we have two regimes if we look at local correlations in this model. One in the bulk and the other one at the edge. Now, what happens at the edge? Indeed, what I showed here is the bulk density. And that's true that in the large n limit, there is a finite support, which results basically from the competition between the confining potential and the repulsive interactions between the fermions. But of course, for finite n, you will have some tail here, okay? So that means that the density will not be strictly 0, and there will be some non-trivial density profile that you can actually, which will be, of course, of the order of the lengths that we discussed before, okay? And so that means that the density will vanish on this length scale, and you can get the density profile close to the edge by using random matrix techniques. In fact, this was done already in the RMT context. This was done a long time back by this very nice paper by Brezin and Bovic, and then Forrester and many other papers computed that. But this density profile, you can get it explicitly in terms of this area function. I'm sure you have seen that before. And if you plot it, well, this is basically what you would get. Okay, so you have to imagine that the density, the Wigner semicircle actually comes here, okay? And although it should be, the Wigner tells you that this is strictly 0, in fact, that there is a non-trivial exponential decay here of the density. And of course, if you now look at what happens in the bulk, then you have this square root behavior, which eventually will match with the Wigner semicircle. Okay, so there is a nice matching between the bulk and the edge, and that somehow says that there is no intermediate regime. Okay, so that's not a proof of that, but that says that basically there is this nice matching between the two. Yes?
So you have this result by using random matrix theory, but for large n, do you think it is also possible to obtain the same result by just doing WKB?
Yeah, okay, yes, absolutely. So, yeah, indeed, yeah. So you can do this, so the standard WKB would only tell you what happens in the bulk, but there is what is called this uniform area, uniform area approximation, where you can indeed have a kind of WKB approximation, which indeed gives you a nice description of your wave functions on both sides of the turning point. So yes, absolutely, yeah. This could be done, and in fact, so we had done that using the RMT connection, but there is one paper that I mentioned by Victor Eisler who actually did that directly with this kind of WKB approach. That's true, yeah. Yeah, absolutely. Right, so many things then can be done. We know that we can, so this was the density, but you can ask about higher correlation functions, typically 2-point correlation functions, more generally n-point correlation function, and we know that we are dealing with fermions, and that tells you that all these correlation functions can be written as a determinant, which involves the kernel, okay? Which is constructed here in terms of this one particle eigenstates, of course. So the object really that you are after is to understand the structure of this kernel, and then you can use the standard theory of determinantal point process to derive many things. Now, of course, this is one way to say the things. That means I'm talking here about determinantal point process, but of course another way of understanding that is just that this is indeed a consequence of the Wick theorem, right? This kernel is nothing else but these psi dagger psi correlations, and we know here that indeed they are given by determinants. So the thing now is that we would like to understand or to describe this kernel in the two regimes that I discussed before. So let's see what happens in the bulk. So when we are close to the center. So if I take 2 points x and y, which are of the order, so this is of the order 1 over square root of n typically, and you probably know that in this case the limiting kernel is simply the sign kernel, which is of course well known in the fermion community, but also of course pretty well known in random matrix theory. Now what happens at the edge is different, and in particular you see that now you have a kernel which is not translationally invariant anymore, and the kernel that you get is actually this airy kernel, which you can write in terms of the airy function and its derivative. Okay, so there is actually another. I'm sorry, Raoul, I'm just erasing this, but let me just write it in a slightly different way. That will be useful for later purpose. Okay, so that's. It turns out that I'm sure you have seen that before. This airy functions kernel, actually, you can also write it in another way, which is simply an integral of the product of these guys. Okay, that will be useful. Now, among as I said, what we would like to understand better or describe better are these edge properties. Now, natural and simple observable to look at to explore the edge properties is to look at the rightmost fermions. Okay, so you would like to say something about the positions, which is the rightmost one. Okay, which has the largest x. I will call it x max. And due to the connection that I mentioned, well, basically this quantity here has the same fluctuations, or this is the same thing in law as the largest eigenvalue of this GUE random matrix. Okay, and this lambda max, I mean, has been studied a lot during the last 15 years, and in particular, it's well known that it is described by the so-called Tracy-Rhythm distribution for the unitary, for the GUE here, and this Tracy-Rhythm distribution actually can be written in terms of this determinant, which so this is a Fredholm determinant here, constructed from this airy kernel here. Okay, so the P of xi here is just a projector. It's just a projector on the interval xi plus infinity. Okay, so that means that if you think about the expansion in trace of this guy here, then typically you will have to compute the trace of, say, p xi k edge psi. So what is that? That's the definition of this. So typically you would like to, in principle, you would like to compute the trace of this guy, and because of this constraint here, you just the trace is restricted on this interval. Okay, so that's. Now it turns out that this guy here, this determinant, and that was actually one of the major breakthroughs of Tracy Widom, and I will come back to this later, can be written in terms of the Perlevée transcendent, and I will come back to that later. But what I just want to say is that it turns out that this Tracy Widom distribution, I'm sure we have heard about it already yesterday. It turns out that this distribution appears in a lot of different problems in statistical mechanics, and this gave rise to a lot of nice developments both in statistical physics, in probability, and it turns out that, as we have heard yesterday in Sylvain's talk, that it actually arises in particular in the Cardar-Parisi-Zhang equation, but it also describes a variety of problems, like some problems, interesting problems in combinatorics, this longest increasing subsequence in random permutations and so on. And to some extent, these free fermions provide one of the simplest physical systems where the Tracy-Widom distribution could be observed. Okay, so that means that it's very simple, right? It's almost a textbook problem, but nevertheless, you can see this nice distribution arising. Right. So that's what I wanted to say here. Okay, so we have seen the bulk, we have seen the edge. Now, there is something that is quite important that I want to emphasize, is that I discussed here mainly the case of the harmonic potential, where I could show that there is a one-to-one correspondence with the GUE. Now, it would be quite natural to ask what happens if I change slightly, if I look at another confining potential. So let's suppose that you have this x to the power p potential. Of course, again, you will have a gas, Fermi gas, which will be confined in the sense that there will be an edge. Of course, for generic potential, the density profile will be different from the Wigner semicircle, and you will lose this one-to-one mapping with the GUE. But nevertheless, it turns out that the behavior at the edge is universal, and that means that it will be still given. If you look at the local correlations, you will find some universal behavior, and this airy kernel will show up again. So that's the paper by Eisler that I was mentioning. This where he used this more WKB type of approaches. In fact, these properties here, I mean, this can also be rigorously proved. I mean, at least to a large extent. This was done by Bornemann for general Sturm-Liouville operator, and not only Schrödinger type. Anyway, that's quite important to have this in mind, that if you have a smooth potential, then you will recover these Tracy-Widom type of things, and so that's quite robust. And the next question that you may ask is, okay, what can I do to break this universality class, or to go to another universality classes? And we know, of course, for instance, in random matrix theory, that the GUE universality class is quite robust, but this corresponds to what is known as soft edge, typically. But we would like later on, we would like to understand a bit better what kind of other universality classes can be observed. Now, although I will not do the full computation as to why or how we can see that this behavior is actually universal, I just would like to give an easy argument, a relatively simple argument, as to why this behavior is universal. And one good way to see that is to look at what is called this local density approximation. So where does it come from? Well, there is a nice way to start, to understand this, is to look at a more complicated object. Instead of the density, you can look at the Wiener function. Okay, that gives you essentially what happens in phase space, so that means in X and P. And the semi-classical approximation that you probably have heard about is that in the large n limit, this will be simply a theta function of this form. Okay, so mu here is just the Fermi energy. Okay, so that's what I have here. And h of xp is just the classical entity, which is here. Right. Now, what is this density? How do I get this density from the Wigner function? This is, you get simply this guy here over Nx by integrating this Wigner function over P. Okay. And when you do this, so it's a simple theta function here. So again, mu is the Fermi energy here. Then you see that when you do this integral, because here you have a p square, okay, then you get immediately this growth. Now, what does it tell you? Well, it tells you that in general, when you look at this formula, it's clear that you will have an edge. Okay, so the density will have an edge, and the edge will be such that v of x edge is equal to mu, your Fermi energy. But it also tells you that in all these cases, you see that the density close to the edge, it will actually vanish always as a square root. Okay?
Gregory, do
yes.
you use any smoothness of the potential here or no?
Actually, this is more general. Here, yeah, this is actually valid even for hard-wall potential or more complicated ones. So, yeah, this for all the potentials that you can reasonably think of, this is valid. So the point indeed is that if this is so, then if you look at what happens near the edge, then you will see that there will be a square root singularity. And it's well known in random matrices that when you have such a soft edge, then you end up with the Airy kernel. Okay, so that's one argument as to explain why we see this universal behavior. Now, of course, the next question is, can we go beyond GUE? Can we see something else? And again, the most natural and also the simplest example that you may think of is simply the hard box potential. Okay, so you put your fermions in a box, okay, and again you just compute the many-body wave function. It's quite simple. It's just some manipulation of determinants. But what is quite nice is that if you do so, this is the positions of your fermions, and if you take the sign of these guys, you get this variable Vj. Then you end up again with a nice random matrix model. And in the random matrix literature, these are known as Jacobi potential. Okay? So that's one realization of the so-called Jacobi unitary ensemble. If you know this ensemble, then you will know that the Jacobi actually has two parameters, and in fact, you can generalize slightly your hard box potential by taking such a v of x like that, some alpha and beta, and you will get the Jacobi matrices. Again, one-to-one correspondence. Now, you probably have heard about yet another ensemble, which is the Laguerre unitary ensemble, or sometimes called Wishart matrices. This can also be realized as exactly the GUE by taking this potential here, 1 over x squared and x squared. Now you see that in these examples, you could expect at least that if you look especially here what happens at close to 0, the behavior might be different from what we have seen before. Okay? And instead of having a soft edge, we would have a hard edge potential, and in this case, we will get different types of limiting kernels. In these cases, one would get the Bessel kernel, which are also well known in random matrix theory. And that means that if you really look at what happens near this wall here, then it will not be described by Airy kernel, but instead this new kernel that I mentioned, this Bessel ones. Okay, I will not discuss this before. This actually was based, the study of this kind of potentials and generalizations was more or less the thesis of Bertrand Lacroix. Okay, so let's move now to yet another generalization, which we had not really, which I think is relatively new. I mean, so again, I want to look at this simple model, again, this non-iterating fermions, and now with some potential V of x. But I would like to say something about, so up to now I mainly focused on the position, so the variables xi's. Now I would like to look at the momenta. Okay. So let's look at the simplest model where I have simply the harmonic potential. Well, then it's clear that in this case, the P's and the Pi's and Xi's, they are identically low, right? I mean, there's the symmetry P squared plus X squared, so they play very similar role. So that means that if you look at the statistics of the momenta, then you will again find GUE. Okay, no surprise. And in particular, if you look at the Pmax, so the largest momenta that in principle you could measure in time of flight experiments, you would find this Tracy-Williams distribution. Okay. Now the question is, what happens if I look at some non-harmonic potentials? So for instance, I mean, in a very similar way as before, I look at this V of x of this form, mod x to the power p, and here I parameterize p by 2n, and I will mainly focus here on the case where n is an integer. We'll see why. But we've seen before that if I look at the positions, I again obtain, if I look at the close to the edge, then I obtain nothing new, right? I mean, I just recover the standard Eric kernel and Tracy-Williams type of fluctuations, so a bit boring in some sense. But if I look at the momenta, the situation is a bit different, right? And this can be seen at this level. This can be seen at this level because now what you will do, so suppose that, so O(n) of x is 2. But now suppose that I just look at something like that. Now, if I want to compute, say, the density in P space now, of course I have to integrate over x. So I need to integrate this theta function here over x. But now things are different, and because of this power here, when you do this integral, it's quite easy to see that what you get is that the density actually now behaves with a different power. So pH is just square root of 2 mu here. It's just Fermi momenta. But the point is that you have now a density which has a different power law behavior close to the edge. Of course, for n equal 1, we recover the square root singularity, and that would give you what you would expect the Eric kernel, and that's what it is. But for different values of n, it's quite natural to expect that you could get some new universality class. So that's what we wanted to investigate. So what you have to do in principle is relatively straightforward. This is the Schrödinger equation that you have to solve in position space. And now, if you want to compute the things in momentum space, that means you simply Fourier transform this equation. So what you see is that this operator here becomes simply a multiplication by p squared. And this multiplication here by x to the power 2n now becomes the differential operator dp to the power 2n. Okay, so that's what you need to solve. And once you have these quantities, well, it's quite simple to show that the pi's also form a determinantal point process, and the kernel, again, you would simply construct it in terms of this quantity. Okay, so the program is relatively straightforward. But of course, now what you would like to understand is what happens close to the, I mean, either in the bulk or at the edge. I will not discuss too much the bulk because the bulk turns out to be, as usual, given by the sign kernel. Okay, and that's very general for determinantal point process. And I want to understand what happens close to the edge. Okay, we have seen before that there is an edge, right? So I'm sure, I mean, we have seen that there is an edge also in momentum space, and we would like to understand what happens. Now the result is the following, is that I will not go through the details, maybe I will give an argument, a simple argument to understand what happens, but so it turns out that we have if you look at the kernel close to the edge, you will have this kind of scaling form here with a typical scale. Mu is the Fermi energy. You can also relate it to n if you want, but it's quite convenient to parameterize it in terms of mu. So that's a typical width around the edge in momentum space. And the kernel, so this is this k area 2n plus 1, see why. It turns out that you can write it under this way. So, that. But now these functions are some kind of generalized area functions, and they satisfy these differential equations. Okay, so that's the 2n derivative of this area 2n plus 1 is equal to, up to some sign, to x times area 2n plus 1. Okay, so if I take n equal to 1, so that means that area 3 in this notation is just a standard area function. Okay? But in general, you will have these more general area functions. Okay? So that's a generalization of the area kernel in terms of these generalized area functions. Now, how can I more or less understand where this comes from? Okay, I will not do it in full detail, but let's look at this equation. What happens is that you want to look at what happens close to the edge. So basically, you will linearize this equation close to p equal to p edge, and at first order this will just be a constant p squared. But then you will have a first term which will be linear in p, and this is morally, this is essentially the equation that you get. Okay. Again, you have these higher order operators, and the p that I derived here by linearizing the p squared term is just the x term that you see here. Okay, this is some decoration, which is not really important. So now we have this nice kernel, and of course we would like to know what we can do with that. Now, what we again would like to investigate, because we have in mind to try to generalize this type of Tracy-Rhythm distribution, we would like to understand the distribution of the largest momentum. Okay? So if you look at the fermions, which has the largest p, and you call it p max, this p, and because you have a determinant to point process, you know already that this will be written as a Fredholm determinant constructed with this k mu here, and we know the limiting form of that guy, right? We have seen that if I look at what happens in the large n limit, this is true for all n, but if I really want to see what happens at large n, eventually I will have a distribution. So this is a cumulative distribution. This will converge to some well-defined function once you have centered and scaled your p, and this f2n is precisely this Fredholm determinant constructed with these guys, this generalized area gamma. So that's nice, that's a bit formal, but now we would like to understand a bit better the structure of this determinant, and for that I will make a detour to this Perlevet 2 equation. So why do I do that? I do that because you probably know that this Tracy-Rhythm distribution, so that means that if I look at the standard Tracy-Rhythm, so that means n equals to 1 in this language, so that will be f2, so the standard Tracy-Rhythm. Well, I've written it in terms of a Fredholm determinant of the area kernel, but it has a nice representation in terms of, so if I look at the log of F2, which is kind of free energy, this actually you can write it in terms of this Perlevet solution here, Perlevet transcendent, which I will. S q squared of q, right? And this q here is the solution of this Perlevet 2 equation, which is well known in the theory of second order differential equations. And this is a special solution such that this, which is known under the name of the Hasse-MacLeod solution, which behaves at the area function for largest. Okay. So that's quite nice. And you probably know, or you may have heard, that of course this is they have these Parevet equations. They have some nice properties, and you can actually, from it, you can actually derive a whole hierarchy of equations, which is known under the name of the Parevet hierarchy, which you can generate recursively using these operators L, which are called these Lennart operators, and you can just enumerate them or generate them in a recursive way. Okay, so if I look at n equals to 1, well, that's just this function here that we have seen. Okay, so G1 is really Q, so this is the top of the hierarchy. And then let's look at the n equal to 2, for instance. Okay, it's getting, of course, it's getting more and more complicated. Okay, but they have some nice structures, and you can actually study them, and there is a whole literature on them. Now, what we showed is that if you now look at this F2n, so that means that if you are now look at the Fredholm determinant constructed with these generalized area functions, it turns out that you can write them in a very similar way as before, so as the standard Tracy-Riedel distribution, but instead here, what you will get is the nth member of the Parevet hierarchy. Okay. So that's one of the main results that we had here. We derived these results using the method of Tracy and Riedel, starting from the Fredholm determinant and deriving by using this machinery, deriving these equations. It was actually so this is a multicritical generalization of this Tracy-Riedel distribution, and we were quite happy that our colleagues mathematicians they actually provided a rigorous proof of this using Riemann-Hilbert techniques, rigorous in the mathematical sense. So Mattia Capasso, Tom Place, and the student, I think. Right. So this was nice. I think. I mean, we can also plot them. So this is the standard Tracy-Riedel here. So it has this well-known. So the blue one is the standard Tracy-Riedel, n equals to 1. It has this well-known asymptotics. Now, if you look at only n equals to 2, actually you start to see some nice oscillations here, which you don't fully understand. But if you compute the asymptotics, so instead of having the s cubed there, you have something which is s to the power 5 by 2. And on the right tail, instead of this s to the power 3 by 2, you have this s to the power 5 by 4. But then you have this modulation by this cosine, which is right. So I still have 10 minutes, okay. So it turns out that these models of this generalization that we found, they were actually they appeared in the 80s, 90s in the context of what is called supercritical unitary matrix models, which are generalization of this Gross-Witten-Wadia model. And I just want to make a short connection to that. So we have to deal here. So let's look at this matrix integral here, where I chose here a very simple potential, which is just a trace of u plus u dagger. Now this model again is very well known, and if I view that as a partition function, it turns out that there is a third order phase transition, which was first discovered by Gross-Witten and independently by Spenta-Wadia. And you can compute, you probably have seen this model here and there, it's a quite famous one. So there is indeed a third order phase transition close to BC, some critical value. And you can say, you could think of analyzing what happens close to the transition. Okay, so you would like to understand what happens near the transition, and to investigate that you use this well-known double scaling limit. And what people have shown after Gross and Witten, in particular Perival and Shevitz and many others, Kazakov also have done some work on this. It turns out that if you look at the second derivative of this guy, okay, which is like a specific heat, if this is the free energy, it turns out that the critical behavior is given by this minus q square. This q here is the Parevet function. Okay. So in other words, this is connected to Tracy-Riedel, and this Steen's-MacLeod solution actually appeared, in fact, already in the 90s, right? So that's well known, and in fact, this matrix integral actually played a very important role in the development of the traceridom and KPZ universality class, because, as you probably know, this matrix integral actually enters into the computations of Dave and Johansson on the longest increasing subsequence. The generating function of the probability that they are after is basically given by this matrix integral. And so that means that this pair that pops out here is quite remarkable. Now, after these models, it turns out that other people in the string theory, mainly community, studied some generalization of these papers. The last one that I found is this paper by Malasena, Klebanov, and Zeiber. So what they were really looking at some generalization of this Gross-Witten model, where the GN is, where instead of having a simple critical behavior, they were looking at some higher singularities. And they were discussing these supercritical models, and they defined a sequence of models here, which are parameterized by Vn, by n here at the end. And there is a whole family of V's. V1 is just the standard one, which would produce the one that we have heard, so the one that I discussed before, which will be eventually given by the standard pair. But they discovered the whole family. So, for instance, the first one on this hierarchy is x minus x squared by 8. So you have to fine-tune, of course, your parameters such that you have a new critical behavior. And with that in mind, what they found is that if you look at this quantity here, it will again have some phase transition around BC, and if you look at the critical behavior close around this transition, well, it turns out that they are again given by this higher order. By the hierarchy of the Perlevet-2 equation, which are exactly the same as the one that we have in our model. Okay, so that means that this traceridom, or generalization of the traceridom distributions that we have found, is actually related to some to these matrix models, and okay, it might open some the way of connection to other models. Okay, so let me just conclude. Okay, so I try to show that there is quite nice edge physics behavior, both in space and momentum space, for relatively simple model of trapped fermions, which we developed essentially using RMT ideas, and in particular focusing on the largest or rightmost fermions, having in mind the connection to the traceridom distributions and its generalization. I've shown that in the simplest case, this is connected to the GUE, Gaussian unitary, but actually more complex potentials, or not complex, but at least the old classical ensembles can actually be connected to this fermion problem. And then I discussed the problem of non-interacting fermions. If you look now at the statistics of the momenta, and discussing the flat potential. Flat by flat, I mean something which is x4 or x to the 6, whatever, something which is flatter than x squared. And we have shown this nice connection with the multicritical unitary matrix model. Of course, the traceridom distribution has been found to pop up in many problems, and the natural question is whether they could, the generalization that we have found, can they be useful to describe other models? And okay, there have been already some attempts to do that. There is a nice paper by Jean-Marie Stéphane who actually have shown that you can actually generate these kind of kernels in spin chains by modifying the dispersion relation. So that means by essentially here adding next nearest neighbors interactions. As I said, these models, in particular the unitary matrix models that I showed you, they are connected to some nice combinatorial problems like this longest increasing subsequence. And so there is some work in progress, in particular in the group group of Jérémy and Dan Bétéa, Jérémy Boutier, Dan Bétéa, more from a combinatorial point of view, who actually have already found some nice combinatorial models which display this multi-critical area type of behavior. And yes, I think that with that I will leave you and thank you for your attention.
Questions? You showed us in the beginning this very nice time of flight measurements, which clearly shows that you can solve the mental distribution.
Yes.
Has this been measured?
Yeah, okay, not yet. So this is something that we are trying to discuss with two groups of experimentalists. One of the problem actually is that you are looking at, so if I look at time of flights, you are looking at the highest values of P's, and there is always the suspicions that these guys with high values of P's, they have not nicely thermalized. So that means that they are not well really described by statistical mechanics, equilibrium statistical mechanics. So that might be one of the difficulties, but in principle this should be doable. So people are starting to think about it. I hope that sooner they will measure something related to this traceability. But at the moment it has not been measured in the experiments, and most of the things that they have measured, again, is mostly related to the bulk. You're right, I mean, you can see that they see something nice, but they have not yet really looked at it in detail.
My next question then would be, is it really zero temperature? I mean,
okay.
Of course it's very low, but on the scale which is set by the Hamiltonian, by the model, I mean, if there are rather heavy atoms, the temperature may be not...
That's true. Yeah, you're absolutely right, so that's another aspect. In fact, I've not discussed this, but we have extended this result to finite temperature. So we know how to compute these kernels and even these whole probabilities at finite temperature too. So in principle, we have the tools to deal with temperature. But of course, the zero temperature limit is probably it looks quite difficult. So temperature plays a role.
Do you know anything about this H statistics for 2D, like for normal matrices?
Right. So yes. So there were some. So we have done some work also on that. So it turns out that they are related to 2D models. So for instance, okay, the model that we have looked at is you look at the 2 dimensions. So for instance, if you look at the trapping potential, harmonic potential in 2D. Of course, in this case, it turns out that it's not really directly related to random matrix models, but we realize that if you start to rotate this, this trap, this becomes related to quantum Hall physics. So, and that's connected to Genever ensembles, and there you can study the H statistics also in this case. That's something that we have done too. Yes, indeed. Yeah. Okay, so that's an interesting question. So in this paper, actually, Jean-Marie, in fact, discussed the effects of interactions for the fermions. He has some kind of argument that says that okay, if you are at the edge, at least at the edge, so the bulk usually is you can do it by some kinds of Luttinger type of effective theory. If you look at the edge, he has an argument, which I'm not sure I can really trust it 100%, but it makes sense. He says the gas is quite diluted, and therefore if it's diluted, I mean the interactions are, to some extent, they play a less important role. Okay, I agree. So that's the thing that in 1D, I mean, this is, I mean, highly, you can doubt of that. So he has some arguments to do that, but the situation is rather unclear. There is, however, one case that you can actually, for which you can say something more precisely, which is the case of 1/x² interactions, because these ones, they are connected to the generalized, to other values of beta for the matrix ensembles. Okay, so that means that basically if you have something which is an interaction which is of the form lambda divided by xi minus xj squared, then if you look at the ground state, then the joint PDF is related to the eigenvalues in the generalized Gaussian beta ensemble. That means that instead of having a van der Monde to the power 2, you will have a van der Monde to a power which is related to the interaction strengths. Okay? And in this case, we know that the edge properties that they have been studied, and they are not given by some other types of traceroidal distributions. So at least we know that interactions in one case they are clearly important. And the understanding of the effects of interactions at the edge in a more general context, as far as I know, is an open problem.
Is the difference if you consider Avogadro bosons?
If you consider yeah, basically this is, yeah, so this is, okay, what he actually is.
Special part is okay, but the momentum is.
Yeah, the momentum is probably different. But for the at least in the Tonsiordo limit, I mean, you will clearly see this in the space, I mean, in real space. Yeah. In fact, these guys, Jean-Marie, I mean, mostly discuss, in fact, this deep linear in the Tonsiordo.
Do we expect that different behaviors if we have some asymmetry of the potential around the bulk, like for example the linear component, or does it like, do we know if it has some the behavior around the bulk contact or in the edge?
Yeah, so okay, I'm not sure I understand your question, but if you already know one this, so for instance here I usually assume that we have a V of x which has a single minimum. Now you can consider some more complicated potentials, for instance with
or simply just add like a linear component to the potential, like.
Yeah, this has not, okay, I would say that it should fall into this universality class, but this has not been studied in detail. Yeah, that's interesting.
Wondering about the case of local dividers, is there anything interesting?
Yeah. So here actually, so we did something with our postdoc, with Naftali Smith. So we studied the case. It's quite nice because there is, okay. So if you have another, well, you have two minima, so that. So now there are two cases that you can easily understand. So for instance, if the chemical potential is very high, or Fermi energy is very high, so if you fill up levels which are very high here, then basically you won't see anything and you will just get the every type of behavior. Now on the other hand, if the chemical, so the Fermi energy is there, then roughly speaking you will have two blobs. Separate ones. And now, of course, you can ask what happens when I arrive here, when they merge. Okay? So that's something that we did, and quite recently. And there is a quite interesting new kernel when these two guys actually merge. This is also a scenario that has been investigated in organometric theory, but the kernel that we find is yet different from the one that you find in RMT, which is usually which is called the Percy kernel. This is yet something else, which you can express in terms of hypergeometric functions. So that's indeed something interesting. Of course, you need to tune a little bit your parameters, right? Because that means that this barrier here has to be high enough. If you have a large number of fermions, it's clear that it has to be. Yeah, so this requires a bit of fine-tuning, but yes, there is also some nice thing here. We have not investigated the statistics of the momenta, but the space properties.
Transition very.
Yeah, exactly. That's what it is.
You have a question? I have maybe a little. Sorry.
So, I know that people are also interested in the edge statistics of Fermi in the context of function.
Yeah, so there are indeed, so in many cases people have also found these traceroidal or airy types of things. Yeah, there is no, again, I mean, in most of the cases, this is related to what I said, is that you have a density which again vanishes as something which looks like a square root, and you find some kind of, not some kind, you find these airy type of things. I've not worked myself on these problems. There are probably some connections, but they are a bit different problems. But you're right. I mean, this has also. I think this has become also an interesting for you guys questions.
Do you try to play with some Calogero-Sutherland models or?
Yeah, so that's
anions or.
Yeah, okay. No, these anions not at all. Yeah, yeah. We would like to indeed. I mean, that's. Yeah, we would like to go a bit beyond this.
Because your lambda or x square.
Yeah, so this one is.
Sounds like anions.
Yeah. So, okay, so this one indeed. Okay, it's a kind of. This one is a Calogero type of model. This one is connected. I mean, at least for the ground state, this one is connected to the beta generalized beta models. Okay, so at the moment, people have not really done so much things with that. In principle, there is now a lot of available results from the RNT side also, I mean, for this generalized beta ensembles. There are probably a lot of things that can be done in this direction. But of course, the computations are also a bit more... but they are there. I mean, in principle, it's doable, yes. Yeah.
So if there are no more other questions,